Welcome dear viewers in this video lecture, and today our topic is radix complement of any number, or simply r's complement of any number. The r's complement of any number is denoted by the number in the square brackets and is given by r raised power n minus that particular number in the respected base. In this equation, r is equal to the base of the number and the n is equal to the number of digits that are present in the number. Therefore, using this equation, we can have 2's complement of any binary number is equal to 2 raised power n minus that binary number. Similarly, 10's complement of the hexadecimal number can be given as 10 raised power n minus n with the base 10. And similarly, 16 complement of any hexadecimal number is equal to 16 raised power n minus n with the base 16. Now, how we can find r's complement of any number in certain base r in a very easy manner? For that, we have to look for the following points. Point number first is that to get r's complement of any number n, we have to start at the least significant digit and we have to proceed towards most significant digit until we find our first non-zero digit. Let us say this non-zero digit is at ith place and we represent this by ai, and up to this AI, we have to copy all the digits of NR. So in other words, we mean to say that we have to copy all the zeros in the least significant side of this N subscript R. Point number second is that we have to replace this first non-zero digit, that is AI, by R minus AI. And point number third is that we have to replace all the remaining digits AJ by R minus 1 minus AJ. To understand the above procedure, consider the following example, where we have to find r's complement of 13 base 10, 13 base 16, and 1101 base 2. Let us first go with 10's complement. As per the point number 1, we have to start with the least significant digit. And here what we find that least significant digit is itself 3, that is non-zero digit. So we have to replace this by r minus 3, that is 10 minus 3. And all the remaining digits are to be replaced by r minus 1 and that particular digit, that is 9 minus 1 here. So the 10's complement of 13 is equal to 8 and 7. Likewise, while finding the 16's complement, we have to replace this 3 by 16 minus 3, and we have to replace this 1 by 15 minus 1. 16 minus 3 is equal to in hex it will be equal to d, and 15 minus 1 is equal to 14, which is equal to e. So the 16 complement of 13 is equal to et. In this similar fashion, we can find 2's complement by replacing this 1 by 2 minus 1, and this 0 by 1 minus 0, and this 1 by 1 minus 1, and this 1 by 1 minus 1, and the result will be 0, 0, 1, 1. So the 2's complement of 110 is 0011. To have a fundamental understanding of r's complement, let us try to observe what is the relationship between the r's complement of a number and the number itself. For this, we will try to observe what is the addition of r's complement of a number and the number itself. So we need to observe this relation. For this, let us try to add 13 and it is 10's complement in decimal number system, 13 and it is 16 complement in base 16, and 1101 and it is 2's complement in base 2. So what we can find is that the addition of all these numbers is equal to 001 here, 001 here, and 00001 here. So we can see here that number of input digits is 2. 2 digits added to 2 digits, we get the result as 2 digits. 2 digits added to 2 digits, we have the result as 2 digits. And 4 digits added to 4 digits, the result is 4 digits. So we can see the result is 0 if we ignore this most significant digit. Therefore, if we neglect carry, what we can see is that r's complement of a number when added to the number itself is equal to 0. It implies that r's complement of a number is actually the negative of that number, provided we neglect the carry. Now we have established the fact that r's complement of a number represents the negative of that number, and we have to really check whether this fact solves the problem of arithmetics. For this, consider the example 13 in base r minus 14 in base r, and we will do this function for r is equal to 10, r is equal to 16, and r is equal to 2. So what we can say that in any number system, 13 base r minus 14 base r will always equal to minus 1. Now in this problem we will use r's complement, that is this expression is equal to 13 base r plus minus 14 base r, which is equal to 13 base r plus the r's complement of 14 in base r. Now 10's complement of 14 is equal to 86. Similarly, 16's complement of 14 is equal to EC. And for 2's complement, we have to first write 14 in binary, that is equal to 110. So its 2's complement can be written as 0010. What we need to require is that we need to add this 10's complement to the 13, 16's complement to the 13, and 2's complement of the number to the 13. What we can see in base 10 is that the result is 99, and in base 16 the result is FF, and in base 2 the result is 1, 1, 1, and 1. But we expected our result to be minus 1. If not minus 1, the result should be 1, and we can see for the sign later. But clearly that the result is not as per the arithmetic. But if we observe the result, the 10's complement of 99 is 1. And if we observe that the 16th complement of FF is again 1, and the 2's complement of 111 is again 1. So you will see that the result is in 2's complement form. But the question is why we have to take r's complement, and where is the negative sign in each case. So till now what we can say that r's complement can be used to represent negative numbers, but what we need is to form a rules of r's complement arithmetics. And second is that we need to take care of the sign if the result is negative in the addition or subtraction process. If you recall, in previous video lecture, we have already used signed magnitude representation of number, and which at that time did not work for us. But we need to roll back, and together that representation, that is signed magnitude representation with r's complement representation, we will see together what they can do. For that, let us retake that example 13 base r minus 14 base r, and the radix are 10, 16, and 2. But this time around, what we will do, we will use sign magnitude form together with r's complement representation of data. We know using signed magnitude representation, plus 13 can be represented as 013, and plus 14 can be represented as 014. And similarly, plus 1101 can be represented as 01101, and plus 1110 can be represented as 01110. Now in r's complement representation, what we will do is that positive number will be represented as same as that of signed magnitude representation. That is, if the number is leading with 0, that is if 0 is the most significant digit of the number, it is positive number. And for negative number, we will be taking r's complement of that number. Therefore, minus 14 in base 10 can be represented as 10's complement of positive 14, that is 986. And similarly, in base 16, it can be represented as FEC, and in base 2, it can be represented as 10010. What we can observe from this is positive 14 is represented by appending 0 in front of it, and when we take the complement, r's complement, in each of the base, we see that the sign bit is changed to the negative, that is r minus 1, that is 10 minus 1 here, and 16 minus 1 here, and 2 minus 1 here, which is really synchronizing with our analysis till now. Now when we add 13 minus 14 in each base, we will get 999 here, F, F, F here, and 1, 1, 1, 1, and 1 here. But you have to note down that these two bits are sign bits. And similarly, in other bases, these two bits represent sign bits. And similarly, we expect that in the result, this is also the sign bit. And we see that the sign bit is r minus 1 in each case. So that means that the result is negative. But the magnitude is in r complement. What we can conclude from the discussion is that To represent data, we have to use both sign magnitude and complement form together simultaneously. The range of R's complement representation is from minus R raised to power n minus 1, and on the positive side it is R raised to power n minus 1 minus 1 for n bits or n digits. Now, if an operation produces a result that falls outside the available range, that is, if n is greater than R raised to power n minus 1 minus 1, or if n is less than minus R raised to power n minus 1, then what we say is that an overflow condition has occurred. This is all for now. Thank you.